Justin Miller, Kirchhoffs Business here. We are going to start looking at some complexities. Ooh, actually, we're going to look at complex circuits. So a complex circuit ultimately is a circuit that has multiple source potentials on different branches in the circuit and forms multiple loops then and requires a special type of analysis. So what we utilize is known as Kirchhoffs laws or Kirchhoffs circuit laws, or sometimes just Kirchhoffs rules. But anyways, what we have here is complex circuits. Kirchhoff, C-I-R-C-H-H-O-F-F. Ooh, I love this guy's name. Kirchhoffs rules for complex circuits. So I should know Gustav Kirchhoff, awesome guy, physicist, mathematician, did lots of cool stuff besides just developing the circuit laws. Also did some stuff with stellar spectroscopy, one of the fathers of that. And you find people pronouncing his name differently than me from time to time. I like Kirchhoff, it just has a good ring to it, but I don't know what they actually called him. Some people say Kirchhoff or Kirchhoff. I like Kirchhoff. Kirchhoff, sorry, Kirchhoff. Sometimes I even get confused with that one. Anyways, potato, potato, I say Kirchhoff, you say Kirchhoff. Big deal. So, consider this circuit. We're going to take ourselves a source potential here. Throw in a nice resistor, come back over here, throw in another source potential, another resistor, close that loop, and then, oh my gosh, we're going to go ahead and put in another one with another resistor and say, what do we have here? We've got an E1, we've got an E2, an E3, we've got an R1, we've got an R2, we've got an R3. And I ask you some simple questions like, hey, is R1 in series or in parallel with R2 and or R3? And your answer is, well, you can't really say. You know why? Because we got these extra source potentials here. We take these out, then it's a little bit easier to say, right? But with these extra source potentials in there, it sort of ruins the notion of individual series and parallel between these different branches here. So you say, well, how are you going to solve the system? Generally, the system says, you know what the resistances are, you know what the source potentials are. Here's a diagram. Tell me what the current through each resistor is, or equivalently, the potential difference across each resistor. Well, before we would say, okay, well, we break it down into equivalent resistance, build it back up, figure out everything along the way, and we're done. That doesn't really work for this, because we've got different source potentials on different branches. So this requires what is known as Kirchhoffs circuit laws or Kirchhoffs rules to be able to solve this. And ultimately there's only two of them, and they're based upon physical principles themselves. So what we want to do is be able to understand Kirchhoffs rules and utilize them to solve out a circuit like this. So this is known as a complex circuit. Complex, and I'm going to say it's a two-loop. Circuit. Why two loop? One loop, two loops. That's how we designate how many loops it has, how many individual enclosures it has. Now there is this third loop that encloses the whole circuit. We don't really count that as the naming loop, just the individual interior loops. So if I added on another one here, it'd be a three-loop circuit. I could add on another one called a four-loop circuit. And there's an importance to that with respect to the rules themselves. But nonetheless, we got a complex two-loop circuit here, and we want to know, how do we solve it? Solve for all currents and or potential differences. Regarding the resistors. All right, so how do we go ahead and do this? Let's make sure that that's actually closed there. Well, we go ahead and start off with what are Kirchhoffs rules or his laws. So we've got ourselves first the Junction Rule, sometimes referred to as Kirchhoff's current law. Anyways, the Junction Rule, nice statement that says the sum of all currents entering a junction must be equal to the sum of all currents exiting that junction. And this is really a statement of conservation of mass and or conservation of charge. We're not creating charge, we're not losing charge, we're creating mass or losing mass. Whatever goes in comes back out. So the question is, well, what do you consider a junction? And a junction, again, is just a kind of fork in the road. It's a split in the branches, where one branch splits off into multiple branches, or multiple branches come together and form other branches. So right here, this would be a junction. I could just call it J1, because this would also be a junction as well, which I could call J2. This two-loop circuit has two junctions. There we go. And each junction has some amount of current going into it and some amount of current coming out of it. So that's what the junction rule is a matter of. So in order to employ the junction rule, one needs to have some sort of concept of what direction currents are going in these different branches. So we've got three branches here, right? We've got this branch, we've got this branch, and we've got this branch. Branch number 1, branch number 2, and branch number 3. And each branch has its own current. All right? So if we know or have an idea or can come up with some sort of directionality regarding the current in each branch, we can write out a junction rule mathematically. So the first step with solving these problems is assign directions of currents in each branch. We'll note it is okay to be wrong. Ultimately, we don't know. We haven't solved it out. We don't know what the currents are. How do we know what direction they're going? Sometimes you can look at something and have a good idea, but sometimes you just don't know. And the best you can do is kind of guess. Well, if it turns out that with Kirchhoff's magic, you don't need to know. You just need to be able to say, hey, I'm going to go ahead and just assign directions. So the first step, assign directions for the currents. Well, let's say this. I'm just going to pick some directions here, and I'm going to say current 1 is going like this. In that particular branch. Well, that I1. And we'll say the current 2 is going like that, upward in that branch. And then we can go ahead and say current number 3 is going like this. So I assign some directions of the currents. Maybe they're right, maybe they're wrong. It really just depends on the source potentials, the orientations, and the resistances. It depends on some things. But nonetheless, I can assign them. Then, can say second, then you write out the junction rules for each junction. Referencing the currents. So we'll come over here to J1 for instance here, in our particular scenario. We have J1. I like to do this just because it's a little helpful. I can just kind of draw the junction like this. There's my junction J1 right there. And I can say, well, what direction is I1 coming into that junction? I1's like this. I2's going up. I can say I2's like that. And what's with the I3? I3's going around that way. So I3's like this. So if I say, what's the junction rule for this? Well, Kirchhoff says it's the sum of all currents entering must be equal to the sum of all currents exiting. What's entering? I1 and I2 are both going into the junction. What's coming out? I3. So the junction rule for this, for J1, would be that I1 plus I2 is equal to I3. There's the junction rule for it. Now if I come over here to this junction, we've got ourselves a J2. I can just trace around what the particular directions of these currents are. And again, we know that this current's going up, that's I2. I3 comes back around and goes this way, in, and I1 is coming out on this side. So we just got to trace it around. The current in a particular branch is the same direction everywhere, so, or the same directional flow. And what do we get with this? Well, we've got I3 goes in and I1 and I2 come out. So for J2, the junction rule would be that I3 is equal to I1 plus I2. Which happens to be this same thing here. So for a two-loop circuit, you only need one junction rule because you just get a reiteration. You get this, a repetition, we'll say, of the same rule. Depending on how many loops you have and how it's configured, you may need one less than the number of loops, or you may have some other correlations where you can start canceling stuff out. You just write out the junction rules. That's it. Take all the junctions, write them all out. But there we go. We got junction rules. Fantastic. Pretty easy to do, right? You pick the current, the junction rules kind of fall into place from there. All right, so what comes next? That's a good question. So the question is answered with, well, Kirchhoff's other rule, and that is known as the loop rule. So number 2, second, I'll say rule, sometimes called laws, but we're going to call them rules. Sometimes called Kirchhoff's voltage law, KVL, but we're going to call it again the loop rule. Loop rule, nice other statement. It says that the sum of all potential differences across all elements in a closed loop must add up to be equal to 0. The sum of all potential differences across all circuit elements in a closed loop must add up to be equal to 0. All right, so what we have to do is understand why would this be the case. Potential differences trace back to changes in potential energy, right? Energy. We have energy being supplied by the sources. The energy is utilized by the resistors. So we have to have that in a closed loop, the sum of all the potential differences across the source potentials and the sum of all the potential differences across the resistors add up to be 0, because whatever energy is supplied is energy that is used. Conservation of energy, that's what this comes from. That's what this is a statement of. Conservation of energy. So, applying this is a little bit different. To apply this, there's an important word there, closed. To apply this, we need to be able to determine whether we call a given potential difference plus or minus, positive or negative. Because we can't add a bunch of positives together and get 0. We can't add a bunch of negatives to get 0. We have to be adding positive and negative, right? That only makes sense. So there is some notion of positive and negative potential differences, but some of it depends on which way we're going around the loop, which way we traverse an element, and what its terminal potentials are. So, for source potentials, we look at the terminals and then the direction we cross. Element dictates the sign. So we know this. For a source potential, the long side's plus, the short side's minus, right? That's the plus side, that's the minus side. If I go across this from plus to minus, the potential difference across it is measured to be negative, right? You go from high to low potential, you have final minus initial, which is low minus high, minus minus plus, which would be negative. So if we go across it this way, potential difference is considered negative. If instead we went this way, minus to plus, potential difference is positive. So it depends on the orientation of the terminals of the source potential and which way you go across them. So you may say, well, what determines which way you go across them? I say, you do. And I'll show you that here momentarily. For the resistors, we get something similar. For the resistors, we have the same notion, except the direction of the current we have chosen dictates the terminal potentials. So I've got a resistor like this, right? What side's plus and what side's minus? Well, it depends. It depends on the current, right? Conventional current is what we deal with here. Conventional current goes from high potential to low potential. So if I say that the current's going this way, that's the current across this resistor. current goes from high to low. Current goes from plus to minus. So I would call this side plus and that side minus. So that's how we determine the terminal potentials for the resistor. We reference the current direction that we chose. Don't look at the source potential, look at the direction of the current that you chose to get the terminal potentials of the resistor. And then it's a matter of which way do you go across it. And then which way you cross it determines plus or minus for the potential difference across it. So if I go across it in the direction of the current, I'm going from plus to minus. The potential difference would be considered to be negative because final minus initial would be low minus high, minus minus plus. If I cross it when I'm measuring the potential differences in the opposite direction of the current, I'm going from minus to plus. The potential difference would be considered to be positive. And that's it. That's the same thing in terms of the terminal potentials that we had regarding the source potentials. The difference is the terminal potentials for the resistors dictated, again, by the current's direction. So those are some things that we need because when we have the loop rule, we need to be able to employ it in a proper manner. So erase this. Here is a closed loop. So I'm going to take this little interior one right here and just call that a closed loop. And I'm just going to draw it out. And there's a closed loop right here. Well, in order to utilize the loop rule, what we need to do is go across all the elements in that closed loop, add up the potential differences, set it equal to 0. But we have to go across all the elements going in the same direction. So, traverse all the elements in a particular direction. Traverse all elements in a closed loop, going around the loop in one direction, being clockwise or counterclockwise. You pick. You can go clockwise, you can go counterclockwise, but you can't go half of it clockwise and then the other half counterclockwise. One direction. And I would just say, just always use the same direction for everything. It makes things easier. Can you do one loop clockwise and the other loop counterclockwise? Yeah. But you can also confuse yourself doing that. So I just always choose clockwise because it works for me. And what do we have in something like this? Well, if I draw in the other portion of the circuit that we have and just concentrate on this one loop that we have, we've got ourselves E1, E2, R1, R2. We set the directions of the currents. We had I1, we had I2, I1, I2 like that. So what we'd want to do is first assign all the terminal potentials for the elements in the given loop. then traverse the loop, adding the potential differences. So, again, for the source potentials, those are easy. Oops. Small ones minus, big ones plus. Small ones minus, big ones plus. So I'm just concentrating on this loop, which I can call loop number 1. And then for the resistors, I look to the direction of the current. Don't look at the source potentials at all. Look at the direction of the current that you've chosen. Current's going to go up through this, goes from high to low potential. Current's going to go up through this one, goes from high to low potential. So once I get all those terminal potentials, then I can start going around the loop and adding up all the individual potential differences. So I generally start one place. Notice that in this one loop right here, this loop, we've got 1, 2, 3, 4 elements. We got to go across all 4 elements. I'm again picking a clockwise direction to go across the entire loop. So I pick somewhere to start. I can call this L1, loop number 1, and I'm going to go across this element first. So, let's get a different color here. This element, I'm going to start here. I go across it like this. I'm going from minus to plus. If I'm going from minus to plus, this would be considered a positive potential difference. Great. Because I'm going from low to high. I go across this resistor now, that's the next thing. I'm going from plus to minus across it. Going from high to low potential gives me a potential difference that is negative, that's right. What do I want to call it? I don't want to call it negative R, that's the resistance. I want to call it negative delta V1, or just minus delta V1. That is the that is the potential difference across this resistor. And the way that I've gone across it makes it minus. So there we go. Source potentials, we use the E's for the EMF, and the resistors will use delta V subscripted with the same subscript as the resistor. Come around, next thing is this one. I go across this source potential here from high to low potential. That means that it's minus, right? So we've got minus E2, then I come across this resistor from minus to plus. That's going to be plus then, delta V2. That's the last thing, I'd be back to where I was, that equals 0. There is the loop rule for that particular loop right there. That's how we do it. Assign the terminal potentials, go across the loop, add them all up, plus or minus. There we go. So that would be for that loop number 1. Well, for 2 loop circuit, we do 2 loop rules. For how many name-wise number of loops there are, that's how many loop rules you'll need. If it's a 3 loop circuit, you'll need 3 loop rules. 4 loop circuit, you'll need 4 loop rules. This is a 2 loop circuit, so we need 2 loops. 2 loop rules, excuse me. So there's actually 2 different loops that we can pick from. I usually stick with these interior loops, the singular small loops, but there's also this outside loop that is a closed loop. Closes back in on itself. That's considered a closed loop. We could use this outside one as well. That would be fine. That could be our second loop, no sweat. But again, I like to just stick with the interior loops. So I call this L2 right there. I'm going to go around it in a clockwise manner again. I've already got these terminal potentials dictated. I need these. This was small, so this is minus. That's plus. The current in this portion of the circuit was out this way. This was our I3, so I3 goes from high to low potential. So this is plus, that's minus, and there we go. We start going across the individual elements. We got ourselves L2, so I'm going to start right here and go like this. I go across E2 from minus to plus, which would be positive E2. I come around. I go across this one from minus to plus. And again, this was E3 to R3 from minus to plus would be plus E3. Then I go across this resistor. That's the next thing. I'm going from plus to minus. So I'd have minus delta V3. And then I come back around and I go across this resistor from plus to minus, which would be minus delta V2. That's the last one. That all adds up to be equal to 0. So, that's what we get. That's what we need to be able to do. Utilize the junction rule to determine or to say what the direction of the currents are, get all the terminal potentials, utilize the loop rules, and come up with these three expressions here. Or enough expressions, enough simultaneous expressions to solve for what's unknown. So what do we have? Well, we've got these delta V's and we got these I's. Really, if we can solve for the currents, we can get the potential differences, because the potential differences across the resistors are just the currents through the resistors multiplied by the resistance of the given resistor itself. So really, we can reduce this down into 3 unknowns instead of seemingly 6 unknowns, because delta V1 is equal to I1 R1, delta V2 is equal to I2 R2, and a delta V3 is equal to I3 R3 via Ohm's law. What do we have then? We've got 3 equations that all involve I1, I2, I3, and we go ahead and start solving them simultaneously. So that just comes down to a bunch of math, algebra really, unless you're using like matrices or something. There's some different ways of going about it. Generally in a class like this, yeah, we algebraically kind of do substitution elimination and solve these out. And that's fun and all, but that's kind of secondary to getting these expressions to begin with. You get these expressions, you're gold, but you gotta get them right. Gotta get them right. And the first step again, assign the directions of the currents. These, sign-wise, completely are dictated by the directions of the currents that you've chosen. You may say, well, they're also determined by which way I run around the loop. Well, what happens if we go around the loop in the opposite direction? What's going to change? All of the signs, right? If I go around this loop counterclockwise, this will be negative, this will be positive, this will be positive, this will be negative. They'll still add up to be equal to 0. It's the same expression. It doesn't change anything. I can multiply this whole expression by -1 right now. It changes the sign of everything, but it's still the same expression because I'm multiplying both sides by it. So that's why it doesn't matter which way you go around, but what does matter is that you utilize the right potential differences, especially for the resistors, when you cross them. Don't look at the source potentials, look at the direction of the current that you decide. That's basically that. Yeah, we'll use some Kirchhoff stuff for some other things as well as time goes on. This is kind of an introduction to it, and that's pretty much that. So 2-loop circuit, we need 2 loop rules, get 1 junction rule, 3 expressions, 3 unknowns, done. Solve, then done. Oh, the one other thing I should say, what happens if you've chosen one of the currents in the wrong direction, which is highly likely. It's easy to do. What happens? Well, when you solve this all out, you'll get that that current ends up to be negative. The value of it's correct, but you just picked the wrong direction. And it's really apparent because it comes out to be negative. What does the negative mean? Hey, it means in the opposite direction that you've chosen. Doesn't mean it's wrong. This means, hey, you picked it in the wrong direction to begin with. That's okay. That's okay. If you want to go redraw the diagram after you've solved everything out, redraw it and have the right directions. But you get all the quantities first based upon what you have to begin with, and then you can make any inferences in determining what the true directions of the currents are. Negative currents, opposite direction than what you chose. That's it. Bottom line. All right, that was fun. Kirchhoff. Yeah, I love this guy. Be well, have a good one, and we'll do a nice problem with this Kirchhoff stuff, so definitely give that a look, because it's easy to write all this stuff down, but actually applying it to a problem may be a little bit more time consuming. Be well, take care.